Hi, this is Sam. I hope my mic's working. This is my Milestone 2 interpreter demo. This is my test environment here. I got set up and I've got some code commented out so I can talk about the tokens a little bit easier, the tokenizing. So I'm just going to have it ask me for some expressions and I'll go in and talk. So for quick demo, I just wanted to demonstrate, oop, yeah, improper token. That's good. Improper. Uh, so this is the sort of structure I'm looking at. And I can pull up the token class here. So this is probably a good place to start. Tokens just have an abstract symbolic type and a value. Um, and the value is a string. So we have a invalid character default case and then cases for letters for typecasting, but typecasting isn't set up yet. Well, it is, but it doesn't work. Um, yeah, that'll be in the future. Uh, Commas are important for um, cell references, parentheses for precedence, square brackets are for cell references, decimal points for floats, TNF for Boolean literals, nums for integer literals, bitwise ops are here, Boolean ops, and then arithmetic ops. So I'll go ahead and plug in like some more this kind of stuff because I think it's fun. We can see it properly recognizing some numbers. That's interesting that these are floats here. I don't know why that is. And then I'm going to end it, and I'm going to comment this out, and I'm going to get back to parsing. So I'll move into the parser first. Well, I'll talk about the lexer first. Um, so I put all this code in one file because originally I was really confused when switching between the files and working on the lexer and constantly having to look back at the token class. So I moved them into one file, and then I got to the parser, and it became really big and really confusing to look at. So yeah, down the line, probably not a good idea, and I'll probably end up moving these into their own separate files eventually. But at the moment, it just kind of helps me stay on track. So here we have a loop where I'm iterating through the expression, and I have a switch case for characters. And in the switch cases, I usually call a helper method, or if it's simpler, I can just admit a token right there, um, like for an arithmetic op or a Boolean literal. But in these cases where I have to check if the following character or the preceding character is the same character, I have some helper methods. Same thing for Boolean operators and bitwise operators, and grid references. So I'll go ahead and show some of those helpers. This is my lex number. So I'm just looping until I stop seeing numbers, and then emitting a float literal or an integer literal, depending on whether or not there was a decimal found. Grid references. So I call this after I've seen the opening square bracket, so I don't have to check for that. I can just capture all the numbers after the square bracket, advance if there's a comma, and then capture the more numbers, and then advance if there's a closing bracket. Then I can emit the token. And at the moment, I'm just emitting the coordinates for the grid reference as a concatenated string, basically, because I didn't want to rework the token class as is, and I can split the string, so it works out okay. And I'm raising invalid grid references here if it's not proper. This is where I had casting set up, but casting isn't working yet. I got that in the future. And this is for compound bitwise and Boolean operators. Or no, this is just Boolean operators. So this is checking if there's a full case of the operator I'm looking for here. Yeah, and this is junk. So I'll move up here to the Lexer and do a little demonstration, or the parser, and then I can talk about it. I believe, yep, we're good. So I can do some arithmetic, can do some bitwise arithmetic, and I'll do a few of those operations just for demo. So 16 bit shift 2 should be 4, like 4 bit shift 2 should be 1, 1 left shift 1 should be 2, right? And we could do some float stuff, huge float and another huge float. Yeah, nice. And it kept the same amount of precision. We can do some compound kind of math, some literal Boolean expressions. Let's demo that true, like true or false. So the syntax there is like pretty similar to general programming languages where it's the double symbol. We can do some logical relations. Yeah, like I don't know. Yeah, that works. And like yeah, and then we could do some like compound stuff where we're like bit shifting and we're doing arithmetic, like probably right. And I've got some error handling for some of these. So if I like did true to the power of true, it'll let me know that it's expecting an arithmetic or a primitive literal there, and it'll close out. And I think it would give me something similar if I did that, like the literal found an op. And you can see here I've got some grids, cells set up, adding these cells to the grid and passing the grid into the environment, and then I'm passing the environment to the parser along. So if I tell it to check a cell that doesn't have anything in it, it'll give me some big error, but it should tell me, huh, ignore that happened. Be like, yeah, invalid grid reference. Okay, that's weird. And I think that's about it for demo. Actually, I can talk about the parser now. So it takes in tokens and an environment, has this index, keep track of, and then parse. I have some preliminary stuff to check. If there's a grid reference immediately, I go ahead and evaluate that grid reference and nothing else. And then this is a loop. This is a bunch of debug code. But we take the first two tokens, or first token, advance, next token, and then we got some conditionals to a lot of conditional statements to check what's going on. So here is like our left branching segment. So that I guess that would be like portions where we're looking at like like this part, if that makes sense. We're looking at like the left side of the tree, or maybe the right. We're looking at one side of it. We convert our values if there's a grid reference, and if there's Boolean objects, we convert those values too. And I also look ahead and check if there's an op done, and we can evaluate that here. Otherwise, we're going to convert our previously found values back into like our abstract types, so integer primitives or float primitives, and I'll check the next tokens and convert them into their proper types. Here we're handling bitwise math, thanking my old self for writing this class the way I did because this evaluate class is just checking uh, which op we have stored in the bitwise expression. So I don't need to do a bunch of like different checks like in the straight up arithmetic and create a whole bunch of different classes. I can just bitwise expression, boom, boom, boom. And it works. So here's on the right branch. We do some error handling and make sure that the tokens ahead are valid tokens. Not that invalid tokens would be passed, but valid tokens given the circumstance in the parser or the context. We do some similar Boolean conversion here and some token conversion here into their abstract types, and then we do some Boolean relations and bitwise relations, and then math here, and then we advance the counter. And yeah, here's the helper methods I used. Most of them are pretty self-explanatory. This one was rarely used. I just wanted to be able to check a certain amount of characters down if there was a certain token for certain expressions. There's similar helpers I should talk about in the Lexer. Um, skip is like advance, except it doesn't do anything. And then advance advances and it does something by returning this character found at that place in the expression. Has next just lets me know there's more room to go. Peak will do the same thing basically as it's like has next plus advance combined. I ended up using that more. Has decimal was useful for the numbers, and here's capture method just to pattern match to the rest of the expression. And yeah, that's about it. Let me know if there's anything I should improve upon. Thanks.